Dear students, today we are going to explain the phenomena of refraction of light on the basis of Huygen's principle, Huygen's wave theory. Well, we have assumed that there is a plane wave front, say ADB, which is incident on a surface with AC which separates the two medium, denser medium from the light, from the medium from where the light is coming, incident on the surface, and another medium in which it shall enter after refraction. The second medium is taken as rarer medium. We also take that velocity of light in first medium is v1 and velocity of light in second medium is v2. As the wavefront needs to be traveling all together, therefore the time taken by light ray to reach from point B to C must be equal to the time taken by light ray to reach from point A to point E. Then only we can have this EC truly representing the refracted wavefront of the incident wavefront ADB. We also assume that angle of incidence is I, that means the ray makes I angle with the normal drawn at the point of incidence. It is also equal to the angle made by the wavefront with the surface separating the two mediums. And also in the same fashion, we have taken R as the angle of refraction, means the refracted wavefront makes R angle with the surface AC which separates the two medium. This angle of refraction is certainly, we all know, must be equal to the angle made by refracted ray with the normal drawn at the point of incidence. Here we can clearly see that the wavefront ED1C will be true refracted wavefront only and only when the time taken by light ray to travel from D to P and further to travel from P to D1 is equal to the time taken by light ray to travel from point A to E or time taken by light ray to travel from B to C in the first medium. And therefore we can write, you see, using the relation S is equal to UT, we have T is equal to S upon U. And that means here you see the distance is dp, that divided by speed of light, that is v1, and then now distance in second medium travel by light is pd1, that distance divided by speed of light in second medium, that is v2. So this is the total time taken by light to reach from D to D1 through P, and this must be equal to the time taken by light to travel from B to C, or we can also say from A to E. So for our choice we have taken that it is time taken by light to travel from B to C, and that will be equal to the distance divided by V1, that means BC by V1. So we call it equation number 1, and this is the condition which if we prove it to be true, then we can say that the refracted wavefront is truly represented by the line ED1C. Now from Snell's law we have the relation refractive index of second medium with respect to first medium is equal to V1 upon V2, and also from the using equation S is equal to 2, we have just discussed we can write BC is equal to V1 into T, and AE is equal to V2 into T. And what is T? T is the time taken by light to travel from B to C, or in first medium, or time taken by light to travel from A to E while moving in second medium. We name it equation 3 and equation 4. Now using equation 1, we can rewrite d1p by v2, we keep it on the left hand side, equal to bc upon v1 minus dp upon v1. We are writing equation 1 in different way. Also dp, we have made some construction over here. We have drawn a line perpendicular on BC from point P. Let it fall at point N. Then it is very much clear, since it is a rectangle, so opposite sides must be equal, therefore we can have dp is equal to bn. And once we have dp is equal to bn, we can write this equation d1p upon v2 is equal to bc upon v1 is already there, minus dp upon v1. For dp we can write b1, we can write b1 upon v1. And so from this diagram what you see, bc upon v1 minus bn upon v1. bc is the whole length minus bn, that means it is equal to remaining part nc upon v1. So we got this equation number 1 rewritten in the form pd upon v2 is equal to nc upon v1. So we call it equation number 5, which is just another form of equation number 1. So if we prove equation 5, then our concept, our assumption that ED1C is the true refracted wavefront will be true. Now from the similar triangle ACB and PCN, you see ACB and PCN, you see these are the two perpendicular 90-degree angles, and this side is this angle is common, angle NCP and angle BCA common, so third angle also becomes common, means this angle becomes common. We can also see the corresponding angles are equal, so these two triangles are having a similarity, and therefore for the similar triangles we can have the ratio of the sides also equal, therefore we can write AC upon PC equal to BC upon NC. You see these two triangles are similar, the bigger one ABC and the smaller one PCN, and therefore we can write from this similar triangle we can write AC upon PC. You see this is AC upon PC and divide equal to BC upon NC. BC, this is full length, divided by NC. So we call it equation number 6. Again we have another similar triangle, triangle AEC and triangle PD1C. These are similar triangles. You have R angle common in them, and this angle D1 and angle E is 90 degree, and so the remaining angle are also equal, therefore these two triangles are having a similarity, and therefore we can again write AC upon PC. AC upon PC is equal to AE upon PD1. AE upon PD1. AC upon PC equal to AE upon PD1. And then you see we call it equation number 7. In these two equations 6 and 7, what you see is we have AC upon PC common in both, therefore equating them we get BC upon NC equal to AE upon PD1. BC upon NC is equal to AE upon PD1. But we also remember the value of BC. Here you see we have value of BC equal to V1T and AE equal to V2T. If you put the value of BC, you get V1T by NC, and for AE you write V2T by P d1, and so T is cancelled on both the sides, so we are left with V1 upon NC is equal to V2 upon P d1. It is nothing but the reciprocal of equation number 5, that is P d1 upon V2 is equal to NC upon V1. P d1 upon V2 is equal to NC upon V1. It is only reciprocated form, so we can truly name it as equation 5. That means equation 5 is proved, and once equation 5 is proved, it means equation 1 is proved, and that means our assumption that E d1c is the true representation of refracted wavefront is correct. Now we need to prove the Snell's law. What is Snell's law? We have already learned that mu equal to sin I by sin r. Now from triangle ABC, you see this is angle I. Angle I is equal to sin I equal to perpendicular, that is BC, divided by hypotenuse opposite to the 90 degree, that is AC. So BC by AC we have sin I value. And for BC we can write V1 up into T, so we get sin I equal to V1 upon V1 T by AC. And from triangle ACE, sin R is equal to perpendicular, that is AE, divided by hypotenuse, that is AC. So that means, and for AE we can write V2T, and therefore we have sin R equal to V2T by AC. Now if you divide sin I by sin R, what you get is AC is common in both in the denominator, they cancel, T is common in both in the numerator, so they cancel, therefore we are left with sin I by sin R equal to V1 by V2, and that is nothing but by the basic definition equal to refractive index of second medium with respect to first medium. And this is how we have also proved the Snell's law. Now it was a great challenge to make the world understand and accept that light is like a wave, and for that the Huygen's principle brought a big relaxation and big comfort for the persons who believe that light is a wave. So I hope you enjoy learning it. That's all for today. Thank you and have a nice day.